In this lecture, we're going to look at Bohr and Schrodinger's atomic models and look at how electrons can be either waves or particles. Be able to define energy level, quantum. We're going to get into the quantum mechanical model a little bit, and atomic orbital will be covered in a separate micro lecture. Be able to relate energy levels of electrons to an element's position in the periodic table. Again, that's the next micro lecture. Compare Schrodinger's quantum mechanical model with other atomic models. That's a big quest for this part of the class. Be able to compare concepts of electrons existing as waves or particles. We're going to do that in this micro lecture, and list situations or models where electrons can be described best as either a wave or a particle. So when is it most convenient to call it a wave? When is it most convenient to call it a particle? Rutherford's atomic model did have some limitations. For example, it couldn't explain why certain things glow. Why do metals glow red and then yellow and then white if you're heating them up? And if you're cooling them back down, they go from white to yellow to red, as we can see on this very hot piece of steel. So what's going on with the interaction of light and heat here? And why do flames burn with different colors for different elements? Why is it that lithium burns with a red flame and sodium with a yellow one? Rutherford's model could not explain this, so a separate one was proposed by Niels Bohr. What he proposed is that electrons exist in different orbitals with different energy levels. So this is a fixed energy an electron can have. That's an energy level, and they defined this as having different amounts of energy between the levels. So in order to go from the k orbital to the L orbital, you would require a certain amount of energy to kind of jump up there. And that amount of energy was a quantum. Now you're thinking, how does this explain how metals heat up and cause, different colors? What happens is when heat is added to an element, such as iron, you're going to end up with that heat being added and causing electrons to jump up a level. Now when they cool down, they're going to go down a level, and as they go down a level, it's going to emit light. And as they cool down, you're going to notice the amount of energy that they're giving out is going to go down. So they go from white to yellow to red. These are lower and lower amounts of energy being released as you are going down fewer and fewer orbitals. So this is Niels Bohr's model, and he kind of put them as rings, so saying that there is a distinct place where it's going to exist. Schrodinger expanded on this using mathematical modeling to create what we call the quantum mechanical model. So this is going to give electrons not as distinct rings, but rather as solutions to a mathematical equation. And this is going to give them a certain function and give it an orbital that is not really a single electron at a single point in time and place with speed, but rather a probability of where that electron is likely to be. Because according to Schrodinger, you can know the speed of the electron, or you can know the location of the electron, but you cannot know both. Once you observe one, you cannot know the other. And we're going to look into those a little bit later. For now, let's look at how we can actually view electrons as particles. The mass of a single electron can be calculated, as can the charge. You're probably familiar with Millikan's experiments that we covered in Chapter 4. This shows that there is a charge and there is a mass, and since there is a distinct charge and a distinct mass for a distinct thing, that thing is a particle. So for doing these kind of calculations, it's helpful to view electrons as particles when you're calculating mass and charge. However, electrons can also be considered as waves. When electrons are fired at a single slit, they're going to pass through the slit and hit a fluorescent screen, causing a certain amount of fluorescence in the back. You can measure this fluorescence and see where the electrons are most likely to hit. Just like firing a whole bunch of bullets at a wall, and that wall has a hole in it, if you looked at where the bullets hit on the backstop, you're going to see most of them hit directly behind the slit. Bullets are particles. The problem with this is when you use two slits, what you would expect is that you would get two distinct bands where the particles would be firing through and would have those bands. And that would be true if you were firing a whole bunch of bullets at a wall with two holes in it. You'll get two distributions of where the bullets are. If you were instead to have waves go through two slits, they are going to not only pass pass directly through the slits, but they're going to interfere with one another, and this interference distribution causes a very different picture than you'd expect with the two slits. So when electrons were fired at a wall with two slits, they created an interference distribution rather than creating just two simple distributions of where they would go through each slit. This means if you're calculating the position of electrons, it's best done during a wave function. So here we have a reason to calculate electrons as waves. Here we have a reason to calculate electrons as particles. And what you can see is, again, these can both be useful depending on what you are trying to do.